Electrical diagnosis. Those two words send many technicians running. But it doesn't have to be that way. Knowledge coupled with experience can help you overcome problems with electrical diagnosis. In this Buick Know-How, we'll take a close look at 3 items: basic electrical tests, strategy-based diagnostics as they relate to electrical concerns, and faulty grounds. Opens, shorts, and high resistance can be checked in a number of ways. When a component is turned on and won't operate, the circuit is open. One way of checking for an open circuit is to perform a continuity test. A continuity test checks that the electrical path through a component or circuit is continuous, that is, without any breaks. Use the ohm meter function of a fluke meter. And connect one of the test leads to the end of the problem circuit. If the electrical path is in good condition, you'll hear a tone when you connect the remaining lead to the other end of the wire or circuit. If you don't hear a tone, and the tone isn't shut off, move the test lead down the circuit until it sounds. When it does, the problem lies in the portion of the circuit that didn't produce a tone. Moving along to shorts, keep in mind that there are 2 types of shorts: short to ground and short to power. And the short to ground occurs when a live circuit grounds out before its intended point. This usually results in blown fuses. A short to power occurs when the insulation chafes away on 2 live wires positioned next to one another, and the conductors contact each other. This crossfeed can cause a component to operate when a completely unrelated switch is used, or will prevent a component from being turned off. The DC setting on the fluke meter can help you locate the short to ground. Begin by disconnecting all the loads in the problem circuit. Use the wiring diagram in the shop manual if you're not sure where they are. After turning the circuit on and making sure battery voltage exists at the fuse cavity, remove the blown fuse and connect the meter test leads to the fuse terminals. Wiggle the suspect area of the harness while watching the meter. When the meter reading changes, the portion of the circuit that was being wiggled is the one that's shorted. Multiple branch circuits, like the tail lamps, interior lights, or power door locks, can be difficult to diagnose because any branch on the circuit can short to ground and cause the circuit fuse to blow. To locate a problem in this type of circuit, review the wiring schematic in the service manual. Using the Riviera's power door lock circuit with a blown fuse as an example, find the first splice after the fuse. In this case, it's splice 312. For more information, see the Fuse Block Relay Center details in Section 8A. The left-hand door isolation relay, door lock relay, left-hand seatbelt release, and right-hand seatbelt release are tied in to splice 312. To physically locate the splice, refer back to the power door lock schematic in Section 8A-131. Then, flip to the appropriate page. Splice 312 is located beneath the rear seat on the left-hand side. To isolate the problem, cut the circuit splice closest to the fuse panel. Then wire a spade-type fused jumper harness into each branch of the circuit following the splicing procedures outlined in Section 8A of the service manual. The jumper wires should be at least the same size as the wire being spliced to prevent them from becoming fuses. When the jumpers are wired into the circuit, install fuses one size smaller than the fuse that protects the circuit, and install an original size fuse in good condition into the fuse panel. Then operate the circuit. The circuit branch that blows the inline fuse is the one that's shorting to ground. If none of the inline fuses blow, the circuit between the fuse panel and the splice is grounded. In some cases, it may be necessary to reassemble the vehicle and drive it with the inline fuses in place to duplicate the problem.
This procedure is effective in locating shorts to ground that occur on an intermittent basis. After locating and repairing the short, remove the jumper harnesses from each of the branches and splice them back into the circuit as they were originally installed following approved procedures.
An unpowered test light can be used to find a short to power. Begin by turning on the power for the problem circuit. The next step is to probe the circuit, starting at the ground side while working toward the load side. In this particular case, the brake lights are on when the parking lamps are on without anyone touching the brake pedal. This means the parking lamp circuit is also feeding the brake lamp circuit. After connecting the test light to a known good ground and checking the wiring schematic, you find power at both the parking lamp and brake lamp feed wire on the load side of the connector. To locate the problem area of the harness, separate the connectors and check for voltage again. Since only the parking lamp feed wire lights the test light, that section of the harness is working as it should. The problem lies in the other section of the harness. To isolate the problem, assemble the connector, then connect the test light to the brake feed wire and wiggle the harness. When the light goes out, you found the short to power. Now, one way to check resistance in a circuit is to perform a voltage drop test. A voltage drop test indicates how much voltage is used by a particular connection, component, or section of a circuit. Voltage drop is directly related to resistance. The larger the voltage drop, the greater the resistance in a circuit. To check for voltage drop in an ECM/PCM ground circuit, run the engine. If the engine won't start, make sure the battery is in good condition and the ignition is on. Set the fluke meter to the DC volt scale. Then, connect the black test lead to the battery negative terminal and use the red test lead along with an adapter to back probe the ground side of the throttle position sensor. With current running through the circuit, the voltage drop should be less than 100 millivolts. If it's more than this, check the ECM or PCM grounding point for looseness and corrosion. If the grounding point is okay, the ground wire may be partially or completely broken. Check for this by wiggling it. If the voltage reading drops, the wire is damaged and requires repair. Strategy-based diagnostics were developed by General Motors' Service Technology Group after observing the work patterns of technicians who had high CSI ratings. They found these technicians had unknowingly followed a similar diagnostic routine, even though they were hundreds of miles from one another and had never met. These diagnostic routines, along with other service considerations, were distilled into the strategy-based diagnostics chart that you see here. Recently, some of the steps in the chart have changed to reflect the introduction of OBD2, which makes following strategy-based diagnostics all the more important. Now, I know some of you may be skeptical about following the steps in the chart in order, and admittedly, in some cases, it may take longer to diagnose a problem following this chart. But the majority of the time, following the steps will save you time and reduce comebacks. The most important thing a service consultant can do is verify the concern. Begin by questioning the customer to see what the problem is, how often it occurs, and under what conditions. To help you get all the information you need for diagnosis, a diagnostic worksheet is included in both the service consultant's and technician's reference books. Your time is valuable, so we'll explain strategy-based diagnosis using 3 real-world situations. In this first case, a customer's Park Avenue will not start, so begin by verifying the concern. Since the car won't start, perform the preliminary checks. Preliminary checks are a basic once-over to help you spot any obvious defects and identify what parts of the system are operating properly. In this case, make sure the battery cables aren't corroded and that they're securely connected to both the battery and starter solenoid. Also, take a look at the battery eye to ensure the battery is fully charged. Since these items are okay, move on to the diagnostic system checks. After finding the problem, which in this case is engine does not crank and starter solenoid does not click, perform the steps in order. The first step is to check that the starter solenoid connections, battery connections, and ground G104 are clean and tight. Since you've already checked the starter and battery connections, check ground G104. It seems to be in good shape. Next, check fuse 2 in the right-hand underhood fuse block. And the fuse is blown. Only a short to ground would cause this type of problem. So check all the wiring in the circuit for signs of chafing or pinching. If the wiring is resting against a sharp object, like the edge of a body panel, chances are the short will be there. If you're not familiar with the harness routing of the system in question, or just need to refresh your memory, review the wiring schematics in the service manual and check the routing of the harnesses in the circuit. In this case, the pink ignition wire for this circuit is pinched behind the parking brake. On closer inspection, the edge of the parking brake cut through the insulation. Since the wire was shorted to ground, you know it was responsible for blowing the maxi fuse. After repairing the wire, tie it away from the parking brake. Then install a new maxi fuse and verify the repair. That illustrates how to use strategy-based diagnostics to repair a simple problem. You didn't have to go through all of the steps, but you did need to follow the steps in order. Now, let's see how strategy-based diagnostics can help diagnose something a little different. The repair order for this Riviera states that the traction off indicator lamp is on steadily. As always, begin your diagnosis by verifying the concern. Sure enough, the lamp remains on after the bulb check. So perform the preliminary checks. This begins with a visual inspection, which in this case is outlined in the service manual. The parking brake seems to be working okay. The major components seem to be in good shape. And all the fuses are in good condition. That leaves the connectors and grounds as the last items to check during the visual inspection. Begin with the obvious anti-lock brake system grounds, which include G104, G201, G202, and G301. But don't forget the less obvious ground, G100. G100 is a PCM ground. However, with the Tevis 4 traction control system, the electronic brake and traction control module communicates with the PCM on the data line to control engine torque when necessary. In turn, a loose PCM ground could set codes 75 and 77, lighting the traction off indicator lamp. And ground circuit G100 is loose. After torquing the bolt to specifications, clear the codes and check for the problem once again. Since no codes are stored, you know you found the source of the problem. Now, let's see how strategy-based diagnostics can help with something a little more complex. This LeSabre is in for service because the door locks work only when the doors are open. To add to the problem, the radio antenna and AC controls work on an intermittent basis. But instead of following strategy-based diagnostics, the technician decides to replace the door lock switch and solve the other two problems later. So, he spends some time over at the parts window waiting for a switch. After 10 minutes have passed, he finds they don't have the switch in stock. Now he has to wait for the porter to go out and get a switch before he can complete the repair. With the right switch finally in his possession, he completes the switch replacement. But after all this, he finds it still only works when the door is open. So he's wasted a lot of time and hasn't fixed anything yet. At this point, he decides to get back on track by following strategy-based diagnostics. That begins with verifying the concern. All of these problems exist, so he moves on to the preliminary checks. Since he's already checked the operation of the systems in question, he needs to check them visually for any signs of problems. The wiring shouldn't be pinched at any point. and the insulation should be in good condition without any signs of cutting, chafing, or burning. As he works, he separates the electrical connectors in the circuits in question and takes a close look at their terminals. They're as they should be, fully engaged in the connectors and free of corrosion. He also checks the fit of mating terminals because he knows that they need to fit together snugly to do their job. To do this, he uses terminals of the opposite sex to prevent terminal distortion. Although larger terminals can sometimes be bent back into position, any poor-fitting micro-terminals should be replaced. In this case, the preliminary checks didn't reveal anything unusual. So he moves on to diagnostic system checks. Since this problem ties into 3 different systems, he'll need to follow the diagnostic system check for all 3. Keep in mind that earlier manuals might refer to a system check or a functional check rather than a diagnostic system check, but they're all the same thing. Unfortunately, the diagnostic system check didn't reveal the source of the problem. So he checks for bulletins. Remember, this includes information available via TechLine equipment, as well as printed bulletins. But no information covers this particular problem. Normally, he would proceed down to step 5.1 and check for any stored DTCs. However, the C67 air conditioning in this LeSabre doesn't store DTCs, and the power door locks and antenna never have. So he moves to step 5.2 in the chart, symptoms with no DTCs. However, with a problem like this one, he knows the chances are slim that a symptomatic chart will cover all 3 situations simultaneously. And that moves him to step 5.3, no published diagnostics. Since there are no published diagnostics, he'll need to analyze the problem and develop his own diagnostics based on his knowledge of the circuit, as well as from other available sources of information, like the wiring schematics in the service manual and any related KnowHow programs. In order to have a problem in so many different areas, there must be a common thread that these circuits share, and this leads him to check the power and ground circuits. Since all the systems that are experiencing trouble don't share power circuits, the power circuits can't be the problem. However, the wiring diagrams indicate the power door locks, radio, and AC control head all share the same ground circuit. In this case, it's circuit G201. And circuit G201 is loose. This very well could have caused the problem the customer experienced. After torquing it to specifications, he verifies the repair. All the components seem to be working normally now. In a situation like this, the technician didn't need to go through every step in numerical sequence. For example, he knew that a symptomatic chart wouldn't cover a situation as unusual as this, so he jumped from step 4 to 5.3. And that's the beauty of strategy-based diagnostics. As your experience grows, you may not have to perform every step in the chart in numerical sequence. It all depends on the problem at hand. And the chances that you'll need to go through all of the steps every time are pretty slim. About 40% of all problems are diagnosed by the time you reach the end of step 3. And your chances of finding the problem increase to about 80% when you've completed steps 4, 5.1, and 5.2. Over the long haul, following strategy-based diagnostics will increase your diagnostic skills, which in turn can help put more money in your pocket. As you can see from our previous examples, grounds are vital to the operation of the electrical system. And systems whose operation is based on milliamp signals, like the ECM, PCM, SIR, and ABS systems, are extra sensitive to their ground circuits and connections. What would seem to be a minor amount of resistance in a ground circuit, caused by things such as corrosion and paint, can have a detrimental effect on these circuits. In effect, it's like having a resistor in the circuit. Consider this. The level of voltage and amperage flow in a particular circuit helps determine the factory calibration of electronic sensors. In turn, The resistance in a ground circuit has a direct bearing on the level of voltage that's available for that circuit. If the resistance in the ground circuit rises above a predetermined level, it lowers the voltage to the sensors in the circuit. In effect, this changes the calibration of the sensors, and everything goes out the window. A ground circuit problem can usually be identified by strange, seemingly unrelated problems like flashing lights along with intermittent operation of various systems and components. Two different tests can check for this problem. The CAM's ground credibility test will tell if the ground is good or not. Or use a DVOM to perform a voltage drop test. Now I know what you're thinking. If you want to check resistance, why not use the ohm meter function of the DVOM? Well, an ohm meter provides very little current during a resistance test, far less than when the circuit is actually operating, and this can lead to inaccurate results. However, a voltage drop test checks the ground circuit with its normal current load, and that will show the exact voltage that's taken up by resistance at a ground connection. Ground G100 is especially critical because it provides a ground path for all components that use an ECM, PCM, or EBTCM ground path. A ground that offers too much resistance will reduce circuit voltage, power that's needed to operate components and allow accurate sensor values. Also, keep in mind that you can't test a ground for looseness by trying to wiggle it with your hand, unless it's really loose. If you suspect a loose ground, tighten it with a torque wrench. Now I'd like to talk to you about one other item: clean and dirty grounds. A clean ground is one that has only minor changes in the current that flows through it. A clean ground is essential for proper operation of electronic components that operate on low current, like the ECM, PCM, and ABS system. A dirty ground is used for relatively high-powered components like power windows, power door locks, and headlamps. Since these components use more current than electronic components, they have a greater swing in the current flow through their ground circuits. Problems arise when the ground from a high amperage circuit is spliced into a low amperage circuit. The fluctuations in the current flowing through the high amperage ground circuit causes the current flowing through the low amperage ground circuit to change. And changes in current flow through the ground circuit can cause sensor voltage values to change dramatically. This can cause all sorts of bizarre problems, ranging from poor drivability to intermittent air conditioning operation. When do these grounding problems usually occur? After improper installation of aftermarket components, such as keyless entry systems, cellular phones, CD players, and alarm systems. So, if an unusual problem occurs with an electronic system immediately after an aftermarket component was installed, see how the component is grounded. Chances are it's the cause of the problem. Now, before we finish, let's pay a visit to Buick's Technical Assistance Center.
Buick Technical Assistance, this is Larry Schramm.
Where strategy-based diagnostics are used every day. The extraordinary is common.
Lightning struck the car through the antenna.
And DCS bulletin searches are a way of life.
What I'm going to do today is run you through the DCS bulletin search and how to log into the system, and we'll do a brief search. All the information that I'm going to talk about can be found in the user guide to DCS technical information, which every dealership has received. And if for any further information, you really should refer to this booklet. It's very good as far as leading you through the procedures. From the terminal menu screen, what we need to do is go down and select iDCS, which is into DCS. The screen here just asks us if our modem is hooked up, and it is, so we'll go ahead. Here we select log on to the host. These phone numbers are already programmed into your T15. Okay, from this screen we want to select BUI for Buick. Select ME for menu on the previous screen, and now we're into the application screen. We want to select TI for bulletins and SPID labels. TI is technical information. And from here we want to go into the technical information search, which is selection 1. we'll go through here and we'll just enter 94, C body, stall. These keywords can be in any order. It doesn't matter which order you type them in. Just make sure that you do stick with the designated keyword list, and that is a part of the manual. Okay, you can see here that we've pulled up 8 bulletins. The number with the W in front of it is a bulletin number. Down further, the number 3 selection there is that's N001487. That is a PI. And you can see on the second line that it says, for additional information, contact your Divisional Technical Assistance Center. And what you would do in this situation is call us with that number, and we'll type it in here and give you the information of what it is. What generally a PI is just preliminary information that will be a bulletin but is not yet a bulletin. We can go in here and select number 1 and display the bulletin. We want to display the bulletin page by page, which is item 1. From here you can page up or page down to look at the bulletin. From the screen here you can type F to scroll forward or B to scroll back. We'll type F and go down in the bulletin a little further. Basically this is just the information that's on the bulletin that would be on the paper copy if you were to look at that. From here we just go back to the main menu, and you can search whatever you need to again if necessary, or other information such as SPID labels and so forth can also be obtained through this screen. The information here that is just a brief overview. For any detailed information you really should refer to the DCS Bulletin Search booklet.
Well, Frank, have you gone through the DCS bulletin search for the dealers?
Yep, we've been through it, Larry. I told them that any other information they may need is in the DCS User's Guide, so I think we're all set here.
Good. If the dealers will go through the DCS bulletin search before they call us, they'll help us to more effectively help them with their cars.
I hope so.
Thanks.
That completes today's program on electrical diagnosis. In this program, we've discussed basic electrical tests. We've also covered how strategy-based diagnostics can help you increase your diagnostic skills, and how faulty grounds can make for some interesting problems. Combined with the information in your reference book, you should now be able to tackle the majority of the electrical problems that come your way, and that will help you satisfy the customer. Take care, and we'll see you next time.
The KnowHow Facts quiz program is now a year old. It is one of the largest facts-type quiz programs in the country. And after some teething problems, it's working smoothly.
Quizzes are received, graded, and returned within 24 hours.
But there are some things that you can do to make it work even better.
First, make sure that you fill out all the information on the quiz form accurately and completely. In order for the computer to grade the quiz, you must include your Social Security number. It is difficult for a computer to read a name, but it can read the numbers by sensing the darkened boxes. Many of you work in a multi-line dealership. In order to receive credit for your quiz, you must enter the Buick dealer code. Then to receive your test score, you must fill in the fax number where you want the results sent.
Getting all the information down makes it possible for Carolyn and the others here at the office to serve you better.